This is going to be a video on Chapter 9.2, which is going to be more about circles, specifically about the arcs in circles. It's going to be covering some new stuff you probably haven't been taught about in circles before. So we're going to start by talking about the central angle of a circle. And this is going to be kind of critical as a starting off point here. So as the name implies, the central angle of a circle is the angle whose vertex is at the center, thus the name central angle. So for example, if this is my circle, bad circle I know, and this is my center, we'll put that C, then a central angle would be something like that. That would be a central angle right there. As would, this right here. So these would both, this one and this one, these would both be central angles. Any angle that has a vertex at the center is a central angle. That's different than something like this. So this right here, that would be called an inscribed angle. That is not a central angle because the vertex is on the center, or on the side of the circle, not in the center. So the center point is like somewhere right there. So this is a inscribed angle. We're looking at these, which are central angles. And as the picture implies here, all central angles should add to 360, because if you add up all the central angles here, here, and even this big one here, they're all going to add to the full length of the circle, or 360 degrees. And now, every time we have an angle, we also have an arc that goes with it in a circle. So we have three types of arcs that we usually talk about. A minor arc, which is always less than 180. A major arc, which is always more than 180. And a semicircle arc, or a semicircle, which is always equal to 180. So these two kind of go hand in hand. These are always kind of off each other. So for example, if I draw a circle here, and I draw a central angle, like this one right here. Here's my central angle. That means that this right here is the minor arc. Right? That's my minor arc there. And then the bigger arc on the other end, so this bigger arc here, that's my major arc. Major. So every minor arc has a major arc, and every major arc has a minor arc, right? They're just kind of two halves of the coin, essentially. Semicircle is the only unique one, in that a semicircle is when you have, well, exactly half a circle. So here's my center, and then obviously this right here, little Pokeball looking thing, that'd be my central angle. I'll call that CA for central angle, right? Or sorry, my semicircle. What do I call that? My semicircle. So I'll put that semi there. That's my semicircle arc there, which is always equal to 180, right? Again, major arc is going to be more than half the circle, so it's going to be more than 180. Minor arc is going to be less than half the circle, so it's going to be less than 180. And a semicircle is exactly 180. And the thing about arcs is that arcs are always equal to their central angles. So for example, if I draw this circle right here, and I draw an arc like this, and let's say this arc is 30 degrees, I could say, or sorry, if I say that this angle is 30 degrees, that means that this arc can also be described as 30 degrees, a 30-degree arc. So you can talk about arcs in the same way you talk about angles, right? So let's look at that a little bit here. So for example, this is my central angle ABC. That means that this arc right here, arc AC, is what I call it. So this would be AC, and you put a little arc over, so you know it's arc AC. That'd be equal to 30 degrees. And this other arc over here, normally if you want to describe a major arc, you add in a third point. It's like right here. They'd say, okay, well, this is point X. And so now you have the arc AXC. That way you know you're talking about the major arc, not the minor arc. Because if I say AC, AC can go this way, or AC can go the major way. So we usually say arc AXC, so that we know we're talking about the major arc, and that would be equal to 330. And the way I got 330 is just I did 360 minus 30 degrees, because that's how big this arc is right here. That's how big that angle is. Is 30 minus the 360 all the way around. That's how much is left for the major arc. Over here we have, arc AC, again in this case would be 70, and then the major arc, arc ADC, would be 360 minus 70, or 290. Okay? So again, just depends on what type of arc you're talking about, and usually we use a 3-letter system for major arcs and a 2-letter system for minor arcs. So always make sure you know which arc you're working with. And of course, we can do a little bit of algebra with this as well. So for example, if I say that BXA is 240 degrees, so this one right here, that's 240, how big is the measure of BCA? Well, again, if the entire thing is 360 and this is 240, that means there's going to be 120 left for this minor arc or minor angle here. Okay? So both the major arc would be 240 and the minor angle would be 120. For this circle over here, again, vertical angles still apply as well. So if this is 50 degrees, that means this x over here is also still 50 degrees because it is still a vertical angle, right? That property doesn't change, which means that this arc AD would also be equal to this arc BE. These arcs would both be 50 degrees. Okay? And these would be congruent arcs as well because they're in the same circle. So if you have two arcs in the same circle with the same central angle, then they're called congruent arcs. So, speaking of congruent arcs, so congruent arcs don't just need to have the same measure. So just because two arcs are 30 degrees doesn't mean that they're congruent. They have to have the same measure, but also they have to be in either the same or congruent circles. So, for example, if I have a circle like this, let's say that I have a circle and that this arc here is 30 degrees. Well, this arc, we'll call it, actually I won't call it a name here because I'm going to be doing a bunch of different arcs. So that arc is 30 degrees. That arc would be congruent to this arc down here because this arc would also be 30 degrees by virtue of vertical angles. So these two arcs would be congruent arcs because they're in the same circle and they both have the same angle measurement. Now let's say this radius was something like 6. Okay? Let's say the radius was 6. Well, that means if I drew another circle, which also had a radius of 6, and I had another arc of 30 degrees here, that arc would also be congruent to the other two. So all three of these arcs are congruent. They're all 30 degrees, and they're either in the same circle, or they're in a different circle with the same radius, which means that it's a congruent circle. So all the same arcs, all the same circle, or congruent circles, and therefore they're congruent. But if I drew a circle like this, and I said, okay, this is a 30-degree angle here, maybe this, is 18 across as a radius. Well, this arc, well, it's still 30 degrees, but I think we can all agree that this distance here is not the same as these two distances here. Now, this one's kind of small because I'm a bad drawer, but again, this circle, 30 degrees on this circle is going to be a much bigger slice than 30 degrees on either of these circles. So this arc, this circle, would not have a congruent arc compared to these two, even though they have the same measure. So that's where the whole same or congruent circles things applies, because you can have a big circle with the same degrees, and therefore the arc would have the same degrees as these two, but it would still not be the same because, again, of the sheer size difference. So this would not be a congruent arc in this little set here. So it's always important to kind of keep that in mind. Now, again, as far as arc addition goes, you can add and subtract and combine arcs the same way you do angles, right? You can like put two arcs together and say, okay, both these arcs together are worth 60 degrees of the circle and stuff like that. So again, they work very similar to angles in that regard. Now, instead of using central angles to describe arcs, we can also describe them a different way. We can describe them in terms of their linear value. So what do I mean by that? Well, let's take an arc here again. Let's draw a big circle. And we'll take this arc right here, and we'll say it's, I don't know, 60 degrees, okay? With a radius of 7, just for funsies here. Okay? So if I asked you, well, how big is arc AC? Right? Well, actually, we'll put this center as C because it's the center, and we'll call this B. So how big is arc AB? How big is it? Well, you'd say, well, it's 60 degrees big. And, okay, that makes sense. But if I were to ask you, well, how far would I walk if I started at point A and I walked along the circle? How far would I walk to get to point B? And you would tell me 60 degrees, which doesn't make much sense. I can't really walk 60 degrees. Degrees is not really a distance that you walk. That's kind of a strange way of saying the answer, no? But right now, it's all we have, right? If I ask you how big this arc is, the only thing you can tell me is that it's 60 degrees, because all we know how to do is relate arcs to the angles. Well, as I said, there's another way of doing it using linear values, and that's called doing it by the arc length, which is why it's called a linear value. And the arc length is basically how much of the circle's circumference does the arc take up, because that will tell you its linear measurement. And the way you get that is you use the following formula. L over 2 pi r is equal to the degree, but DEG here, the degree, over 360. Or again, if you remember, 2 pi r is basically the circumference formula. So you can also write this as L over C, circumference, is equal to degree over 360. So as long as you know the circumference, you can use this formula. And as long as you know the radius, you can use it as well. It just depends on which one you want to use. But again, think about what this means here. This is asking you, okay, 60 is what percent of 360? That's what this fraction right here is representing. 60 degrees is what percent of the 360 degrees total, and you want to relate that to how much the length of the arc is compared to the entire circumference. It's almost like a percentage thing. 60 is what percent of the circle, which means that this arc is what percent of the circumference. If 60 is, if we do some quick math here, 60 is 16% of 360. So 60 is 16% of the entire circle. Well, then wouldn't it make sense that this arc is 16% of the entire circumference? So the circumference of this circle is what? Let's do the formula here. 2 times pi times r is 43.98. Well, that means that this arc is 16% of that. So if I times this by 0.1666666, just all the way across there, I get about 7.3. So this arc right here is about 7.3 units. I could have put like inches here and make the 7.3 inches if you want to, but it's whatever linear units across. That's how far you would walk along this arc here, is about 7.3 inches, centimeters, meters, whatever the unit of measurement is. So it's just another way of describing how big an arc is without using the degree measurement, but actually talking about how big the actual length of the arc is, which is why this is called the arc length. So this L right here is called the arc length. Okay? And the degree is obviously the central angle degree, or the arc degree. So let's look at this example here, okay? See if we can't figure it out. I want the arc length of AXB, so this arc right here. Okay, well the central angle is 110, so how I would do it is I do this. The arc length that I want out of 2 times pi times r, which is 8 in this case because r is the radius, is equal to 110 out of 360. So first thing I would do is figure out, well actually you can type this all in at once here. I'll show you how to kind of do it all at once in your calculator just because there's going to be a lot of decimals floating around that I don't want to bother rewriting. So 110 out of 360. So this is 0.305 repeating. Actually, I will write it out. 0.305 repeating is equal to L over, let's figure out what this junk down here is, 2 pi 8. So 2 times pi, pi times 8. 50.265. 50.265. Now, I need to figure out how big L is. Well, in order to figure out how big L is, I would simply multiply both sides by 50.265, right? So I'm going to take 0.305555555 and times it by 50.265. I get 15.358, or if we round it, 15.359. So L is equal to 15.359. And there's my answer. Right, that arc is 15.359 feet, not degrees, but feet across. Which again makes sense because it's a large part of the circle, so it makes sense that it makes up a decent amount of the um, arc there, the circle there. It's not quite half because it's not 180, but it's a pretty decent amount, right? If I want the arc length of BYA, which is the other part, well, I did it the same way. Arc length over, now the circumference isn't going to change, so this is still going to be 2 pi 8, but I'm just going to put down 50.265 just to save some time here. And then the degree of BYA, remember, if I want BYA, which is this right here, I'm going to have to do a little 360 minus 110. So 360 minus 110, which is what this minor arc is up here, and that'd give me 250 degrees across. So then I would figure out this formula here. So I'll go ahead and do this in my calculator quickly here to save some time. So 250 over 360, and then times that by my bottom part here, 50.265, and we get about 30.9, 34 rather, 0.906. So let's see here, 34.906, 34.906, and that is my arc length. So again, it's no real big difference from measuring it with degrees. It's just a little conversion you have to do, and it gives you the linear measurement across rather than the degree measurement of the opening or whatever. And then there's one last thing we need to talk about angles here, and that's about the different types of way to measure an angle. So angles have their actual own unit measurements besides degrees, and that's called the radians. So you can measure angles in terms of radians, not just degrees. So a radian is basically a comparison of the arc length to the radius. And that's how big an angle. So you're telling me how big the angle is in terms of how big of a arc length that it makes. So rather than telling me an angle is 3 degrees, you're going to tell me how many radians, which is basically going to tell me how big of an arc the angle is going to make on the circle. So for example, a radian is basically one radius. So an angle that is one radian open has an arc length that's equal to one radius across the circle. So if the radius was 7, an angle with one radian makes an arc length of 7 because it's one radius across the circle's circumference or over the circle's circumference. Now, luckily for us, even though it sounds kind of complicated, there's a fairly simple conversion. To get the radians, you're going to take pi over 180 is equal to the radian over the degree. So if you have the degree, you can find the radian by simply plugging the degree number in here and solving for the radian. And vice versa. If you have the radian, you can plug the radian number in here and solve for the degree. So this conversion here is how you can go between radians and degrees fairly quickly, right? It's not that hard of a conversion, hopefully. And again, this pi over 180 kind of represents the truth that pi is essentially 180 degrees across the circle. So if I have a circle right here, that means that this angle right here, this semicircle, has a angle measure of pi, right? That's pi, that angle is pi units big, pi radians rather, I should say, big, because it's 180 degrees or halfway across the circle. Because remember, a full circle is 2 pi, right? That's how you get a full circle circumference is 2 pi r. So 1 radian is going to just be pi, because it's just half that. And so if we want to get the arc length using a radian measure, it's slightly different, but the formula goes like this. I'm going to use the theta here for the angle measure. So theta is equal to the arc length over the radius. I don't want to use rad because people might think this is short for radius, so I'm going to use theta here. So theta is the angle in radians. L is the arc length, which is usually what we're trying to find. And then R is the radius. Okay? So using this formula here, you can figure out how big the arc length is as long as you know the angle's unit in radians and how big the radius of the circle is. So let's look at an example here. And radians are usually given to you in terms of pi, because like I said, a circle's full circumference is 2 pi r. So it makes sense that we're going to talk about radians in terms of pi, because again, they're talking about how far across the circle's circumference that you go. So this is my angle measure in radians, pi over 5. This is my radius right here, 4. I want to find out how big the arc length is. All right, fairly simple enough. So we have theta is equal to the arc length over the radius. So pi over 5 is equal to x over 4. Right? Again, theta is pi over 5. 4 is my r. I just simply swap them in. X is my arc length. If I want to solve for x, I multiply both sides by 4. So I get 4 times pi over 5 is equal to x. That's it. Now, you can actually leave your answer somewhat like that, or you can leave it like this, 4 pi over 5. That's called leaving your answer in terms of pi, because we can see the pi in the answer there. It's right there. Actually, I kind of bolted over there, but we have, let me try it again, 4 pi over 5. Right? Or you can actually multiply this out to get the decimals. So you actually can do 4 times pi divided by 5, and you get 2.51. 2.51. So either of these answers work. This is the answer in terms of pi. This is the answer as a decimal. But they both tell you how big that arc length is. It's 2.51 inches across, or 4 pi over 5 inches across, depending on however you want to say it. So that's it for this lesson. Again, it was a lot of kind of new stuff about angles, so make sure you if you need to look it over again, that's fine, but make sure you give yourself time to practice and digest this. As always, let me know if there's any issues, and hope to see you soon.